Okay, we're going to talk about distribution system flushing now. The flushing we're talking about is not something you do in the toilet, right? It's something about opening up fire hydrants to improve water quality. So that's where we're starting as a basic assumption. So why do we go out there and flush? Okay, well, the main reason that people use it for is to scour any deposits and possibly films along the inside of the pipe. And the second reason is that it can pretty quickly improve the age of water, which will correct low chlorine, and it could also move water that has poor taste and odor out of the system. So there's some quality, existing quality ones as opposed to just dirt and turbidity. So there's really different kinds of flushing reasons. Or sometimes people just go out there and do it when there's a complaint. It just shows the people that live there, hey, we're doing something. If you have dirty water or taste and odor, a good thing that, knee-jerk reaction is to get out and flush because it probably, in a lot of cases, is a good thing to do. It'd be better, though, if we tie this in with modeling as well to get a better handle on how this actually should work. Okay. And also people flush, their main purpose could be to test hydrant operation. There are some places where we talk to the people about, well, why do you do your flushing program? And their number one reason is we want to get on every hydrant every year to make sure it works. And that's our number one purpose. If we improve water quality along the way, that's great. That's our second purpose. But we're really there to make sure that when a fire truck pulls up and it starts to operate the hydrant, that it really is working. So there's a lot of reasons that people go about doing flushing of water systems. How's it done? Well, you usually identify some location, open up the hydrant or blow-offs, and flow until the water quality improves, or maybe you reach some time limit that you set for yourself. The general rule of which ones you flush in which order, I go back to Tony Gangemi's law. This is a guy I worked with for quite a few years who was the head of operations. And his rule was always flush with clean water behind you. And that makes good sense. You don't want to do things where you're moving dirty water into an area. You want to start flushing. If you are doing multiple flushes, start with the cleanest water and keep pulling the fresh water with you behind you. Basically, you're dragging the fresh water along as you move from one hydrant to the next. There are places we've worked, like right where I live here now, that they do not do flushing during the day because it's a chance of stirring up some sediment in the pipe and increasing turbidity. So they do the flushing at night. And there's also like, when do you stop? When is clean enough? That becomes another question if you're flushing to remove turbidity. So this is just a general overview that even if you don't use any kind of modeling, you'll want to obey basically these basic rules. Now, overall, there are two kinds of flushing that one we'll call conventional flushing, where you essentially open up one hydrant at a time. You're not operating any valves or anything like that, and you just march through the system one hydrant at a time. The second type of flushing that we talk about is what's called unidirectional flushing, and I'll say UDF at times during this talk. In this case, you're trying to flush and clean a specific run of pipes. In that case, you want to close valves to make sure that the water going to the flushed hydrant is going in exactly the direction that you want it. Now, you may also use multiple hydrants as well. The benefit of unidirectional flushing is that it increases the velocity, which increases the shear stress and you have a better chance of getting the solids out. You get higher velocities. Downside is that it's more work. It's more work in planning and more work in the actual carrying out of the flushing. So I heard a good talk last month at a conference about this, about how much more work was involved. There's quite a few hours per flush involved. So that where the conventional flushing, you can do 20, 30 hydrants a night. Unidirectionally, you may be able to get 4 or 5 because there's just so much more stuff involved with it. So there is a trade-off here between the extra velocity and the extra work that you have to do. The real criteria really isn't so much velocity. People talk about velocity because they can understand it better, but it's really the shear stress along the pipe. Now, shear stress, again, is stress parallel to the direction of flow as opposed to pressure, which is force going outward. This is force on the particles parallel to the direction of flow. And really, this is the criteria. But generally, people talk about velocity because even I do. I can visualize velocity and think about it more than shear stress. So what indicators do you use? Well, usually you want to see what's the maximum velocity that we got in the pipe. And we do in WaterGEMS and WaterCAD is save the velocities for all the pipes in the flushing run so that you can see, did we get our target velocity or target shear stress? And what you do is, you usually, when you're setting up a flushing program, you usually do it in by areas in a given set of pipes at a time. You don't want, if you have 20,000 pipes in your system, you don't want to do one run to do 20,000 pipes because you can't really do 20,000 pipes in a night. At least I haven't figured out how to do that. So what you usually do is break the work into sets of pipe, areas where you're going to do one day of work. And you do that one day planning, and then that's done. And then you can go on and plan the second day of work and the third day. And that's generally a good way to do this because especially with unidirectional flushing, it's a lot of work setting it up, and you don't want to start out and do 10,000 pipes at one time. We also in WaterGEMS, they'll give you the ability to compare across runs. You may be trying to flush a pipe, but that pipe may already been flushed pretty well with the preceding run, so you can make those comparisons. Now here's kind of my view of flushing velocities. Okay, this graph here, the horizontal axis is your normal velocity, or maybe your high every day you get to a certain high velocity. Okay, the vertical axis is the velocity you get during flushing. So we have several different regions in here, and we'll go through each of those regions. I mean, you want usually 2.5 feet per second is kind of, I'll use as a typical number that you want to get above to clean out the pipes. You want to get above that kind of velocity. And if you're running 2.5 feet per second normally, then that pipe is probably clean to start with. There hasn't been very much chance of much stuff settling out in the first place. So let's look at some of these regimes here, okay? Down the yellow range here, where the yellow dot is, that's where the velocity gets slower when you're doing flushing, and that's not very likely, so that area is grayed out. If the velocity only increases a little bit, the orange dot, you're probably not getting very good scouring if you're only increasing the velocity in the pipe slightly during scouring. If you're in the green range, where the green dot is, that's the range where the scouring you're getting from flushing is really effective. You've taken a low velocity pipe that doesn't have much shear stress, and you're increasing it significantly. And that's where you get the best benefit of flushing when that happens. On the other hand, if you're where the blue pipe is, the blue dot is, you probably don't need to flush those pipes. So one of the things we recommend is before you even run it, just run an EPS model. Look at what the highest velocities are. You may find pipes that have really high velocity every day. So there's very little chance that you need to bother flushing those pipes. Then you get up into the red range where I ask the question of, do you really need this kind of velocity? Because people try to specify, this is the minimum velocity you need for flushing, but I've yet to see a really good study that says this, you must get this velocity. It's more a matter of getting the velocity higher than it usually is. Well, there's been some research on that kind of shows that increasing the velocity to a higher one, significantly higher than you have in a normal day, is the real goal. So you want to get above that greenish dotted line. So it's not so much, you may be able to flush the pipe pretty effectively at 1 foot per second, possibly, if that pipe is one that has like zero velocity most of the time. So it's not a definitive answer. There's some people say that, well, you can actually scour out biofilms if you get up around 10.9 feet per second. I've yet to see the definitive study of this, although we've been in a number of discussions with people who swear that they can remove biofilms at higher velocities. So that it's still an area that it's not totally clear of just what the target velocity ought to be in general. But usually, if you can increase the velocity by a few feet per second, you're probably doing good, or increase it by 0.5 meter per second if you're in a metric country. Okay, so what should the value? Well, depends on what the material is you're trying to move out. If you have just loose sediment in the bottom of the pipe, which is most of the time what you have, you just need to increase the shear stress. If you have manganese deposits in the pipe, you may need to increase a little higher because this is kind of loosely attached to the pipe wall. Calcium carbonate scales, if you have water that has a very high saturation index that's going to make the calcium carbonate precipitate out at pipes, then you need a higher stress. Now, I've worked in one place where they had a lot of history of doing lime softening of the water and then not recarbonated. So they're putting out some really high pH water that forms scales inside the pipe. And the scales weren't nice, smooth scale like you'll see in some pictures. These were like, we call them shark's teeth. They were little jagged scales that you would form. And after you did a flushing, you could walk out in the street and actually see these pieces of little white pieces of little shark's teeth laying out in the street where the calcium carbonate scale came out. Now that one was more of an unusual system, but it did happen. Old rusty pipes have tuberculation inside of it, and you usually cannot flush tuberculation out. I've heard people imply that you can do that, but it's usually not flushed because tuberculation is attached to the pipe. Biofilms, like I said, we really haven't, I haven't seen the definitive study that shows you what velocity you start to affect biofilms. And if you're not sure, what you can do is, run some tests. Start the flush at a low velocity, maybe a foot per second above normal, then go to 2 feet per second, 3 feet, and see what kind of material comes out. You'll get to a velocity where you're not scouring anything. The other test you can do is if you're having, say, nitrification in a given run of pipe, and you suspect it's due to biofilms, do a test study in that area, a pilot study, and then go back later and see, are you getting nitrification again in a pipe, especially in chloraminated systems. Okay, so shear stress is the real criteria, and that's the formula that we use to calculate shear stress in WaterGEMS. And it's can be simplified down to a function of velocity, so it's related to the velocity, but it's not a linear relationship to the velocity. And stress is measured in pounds per square foot or newtons per square meter or pascals. And in English use, therefore, you can see that the shear stress related to the velocity, but it's also a function of the diameter. It's harder to get good shear stress in a bigger pipe. Now, let's get to the model. Okay, so should you model the hydrant as just the junction that's close to it? Is that the correct way to model it? And in general, yeah, that's the answer. Most hydrants are located near intersections, and I've done some analysis of how much different it is if you treat the hydrant as being at the junction node versus treating the hydrant as including its lateral and all that. And for the most part, when the hydrant is close to the intersection with a reasonable small lateral, using the junction node as the flushing node is good. Now, if you want, we have hydrant elements that you can place them at the exact location of the tap. And you can actually assign the lateral losses to the hydrant element. And that is a little more accurate. Like I said, it's not tremendously different, but if you want to get down to that level of detail, you can do that. Or if you really want to get precise, you can actually put in the hydrant lateral. Instead of including the losses with that hydrant element, you put in the hydrant lateral itself, and you get the most accurate answer, but whether it's worth the extra effort is up to you to decide. Now, it's important, though, when you're doing this to understand when you're using unidirectional flushing, it's important to understand where the closed valves are. Like for conventional flushing, what I just said in the previous slide is always true. For unidirectional flushing, it depends on where isolation valves are. So, for example, if you have an isolation valve between the node and the hydrant and you're going to close it, well, that's a very different picture than flushing the junction node. So if you're going to be doing a lot of unidirectional flushing where you're really going to get precise about this, then including the isolation valves and the exact location of the hydrant is important in your model. So what should the hydrant discharge be? How do we handle it in the model? Well, you could specify the flow in flow units, whether it's GPM or liters per second. You could say this hydrant will flow 500 GPM when I open it. That is nice and direct and simple. We all understand GPM units, but hydrants on big pipes are going to have a lot more flow. Pipes that have a very high pressure as a static pressure are going to have more flow than those that have lower pressures or lower pipe sizes. So the more accurate way, and a way that I recommend people do, is to specify the emitter coefficient for the hydrant. Okay, so this is a number. It's actually GPM per square root of PSI is the units. And I went through and recommended some values for those emitter coefficients. So what I did was I took AWWA standard C503, which specifies the amount of head loss you can have in a hydrant, and looked at what kind of emitter coefficients that corresponded to. Now, the lowest flow you're going to get if the hydrant corresponds and complies with C503 is going to be the emitter on a 2.5-inch outlet. It's going to be 150 is going to be the emitter coefficient. And if it's the 4.5-inch that you're opening, it's 380. So that's a hydrant that barely meets the AWWA standard. If it's smoother on the inside and is more hydraulically conducive, you can get higher values. So even this is kind of a guesstimate too. But I think it better accounts for the fact that the flows you get out of the hydrant depends on where the hydrant is. Thing is, don't specify both when you're in there. Don't specify this is the flow I'm going to get and this is the emitter coefficient, because then you're going to add them up, which is not right. Some terminology about how we handle flushing in WaterGEMS is that we talk about an event, okay, whether it's conventional or unidirectional. This is the one flush. Some people call it a sequence, okay? And then we talk about areas. This is an area I generally recommend people use each area as like a day's worth of work that they estimate. Okay, this is what we plan to flush this area, and we use that term to as a breakdown so that you don't have to do the whole model at once. And then within that, you may be doing a study, maybe doing 4 or 5 days that you want to study a problem area. So study is a group of areas together, and a study can have one area in only. A pipe run is the pipes that are included in unidirectional flushing that you're targeting to flush. You target a pipe run as what you want to flush. That's what we check. And a pipe set or nodes of interest are things that you want to store data for. If you've got a 20,000 pipe model and you're flushing over in the far southeast part of town, the northeast and the northwest and all, they don't get impacted. So rather than storing data for pipes that are totally irrelevant to the flushing, you define a pipe set for each area. And these are the pipes I'm working on in this area. And scenarios, you have a representative scenario. This is the underlying hydraulic condition when I'm out there flushing. This is what I expect my tank levels to be. These are the pumps I expect to see running while I'm doing the flushing. Output scenarios are the ways to view individual flushing events. So the steps in conducting a flushing study go something like this. Calibrated model should be your starting point. Okay, if you don't have any faith in your model, then you're not going to have too much faith in your flushing results. So we get into the flushing manager, which you get under the dialog for flushing. Then you create a study, this is the top level, then create the area and set up options as to what the target velocities are and what's in the pipe set. That's where you set up that in the area. And then you go through and create the individual events, and then you can compute. You can compute an entire study at one time, you can compute all the pipes in an area at one time, or you can compute one event at a time. Now, we have several ways to look at the results, okay? One is to go through with the flushing browser, which goes through flush by flush, event by event. The flushing area report looks at it pipe by pipe, and that's another way to look at it. Or you can create an operator report. This is usually the goal of a study, and what you're doing there is you're putting together something that you can hand to the maintenance operators who are going to go out and do the flushing and say, here's what you're supposed to do on Friday. This is your report today, and they list specific instructions as to what hydrants to flow in what order, and if you're using UDF, which valves to close, when to close them, when to open them. So I'll show you an example of that a little later. Okay, so let's look at this. So what you'll see when you get into the flushing manager are flushing studies. We have 2 flushing studies here, and we have flushing areas under as a subset of it. And you can give them names to the areas. So it's not just study 1, area 1. You know, those are not very good names. You eventually forget them. So it's good to give it some names, like, okay, the area around Martin's house or something like that, whatever you choose it to be. So within the area manager now, this is where you set a lot of the settings for a run, okay? What scenario is going to be our base? This is the first thing you set. Where do you want the results to go in the output scenario? And what's our target in terms of velocity and shear stress? Which pipes out of this whole system, which pipes do we really want to study? We want to not store a lot of extraneous data for the other pipes. And which nodes are of interest? Because one of the things you're interested in is not pulling the pressure down too much. Because when you open up hydrants, what happens to the pressure in the area? It drops. And when it drops, you don't want it to drop too far, or else you're going to have other problems in the system. So you can also specify what nodes are of interest. And then here's where you can specify the flow demanded or the emitter coefficient. As I said, pick one or the other. And then do you want it to be added to the baseline demand, or do you want it to replace the baseline demand at that node? Usually I say add. Now I have some optional things down here that you can store auxiliary output. Now these are values that are not necessary for the hydrant flushing, but they give you, they'll save some data on any node that has a pressure less than 20 will save. And any pipes with velocities greater than, let's say, 2, or maybe you only want to see really high ones. This is in addition to the pipe set. We'll store those values so we can make sure we're not drawing the pressure down. And if we are drawing it down, what pipes is causing all the head loss? Okay, so those are results that aren't necessary, but they're nice results to have. So as you set up your area now, so the targets are set up in the green boxes, and these outputs, extra outputs are controlled down here in the blue box. So what does an event look like? Okay, so that's the basic unit of work. Conventional flushing basically is what hydrant do we flow? It's pretty easy and conventional. For UDF, it's which hydrant or hydrants do we flow, and which pipes or valves do we close. Now, if your model has valves, it's a lot better off. Otherwise, if your model is based on pipes, it gets really tricky when you're flushing a hydrant on a pipe and you've closed a valve on that pipe. what side of the closed valve is that hydrant on becomes a question. And you pretty much almost have to, you know, specify the valves if you're doing UDF, because doing it by pipe can get really tricky to do. Now remember, in a individual run, you could run by area or by study, so you can run multiple events at the same time. And they could have labels. The default labels are, flushing 1, flushing 2, flushing 3. Again, I encourage you to use better names than that. That's just the default name that we give it because we got to give it some kind of name. But we'd like you to say, this is Pine Street near Apple Street, something like that. Okay, so the Events tab now, when you click on Events at the top, you have Options, then Events. Well, now is where you specify exactly which hydrants or which events are going to be run in this area. Okay, so we're going to, in this case, we're not going to run. We've decided that 4 and 5 were not really that important in that list. And so we're not going to do those. We're just going to see what the program will look like if we only do 4 out of the 6 hydrants. And we just make them inactive by unchecking them. So here's what an event might look like in unidirectional flushing. So here we've gone in and closed off several of the isolation valves so that all the water going to this hydrant goes through the pipes that now become orange, because they're the ones that are in the run and they're the ones we want to flush. We don't want water coming in through the back door. So there's your event hydrant, and those are the valves that you need to close for a given event. So what it looks like now in the event manager, it looks something like this. So we say, okay, which valves are closed during this event? Which hydrant are we opening? And which pipes are in the pipe run that we're trying to clean? Now, this is the way, generally you're going to be working here in the right pane. So, and up here at this little arrow at the top is how you can add another element. Over in the left pane, it looks sort of like this. These are just some simple visualizations. These are all the valves that are closed now. This is the hydrant you flow. This is the pipe run. So we've had some other isolation valves that were closed for other reasons in the system. So it's the location of the event. That's the flowed hydrant. Those are the closed valves, and that's the pipe run. Okay, so we've done the calculations. We hit compute, we've got results. What do the results look like? Okay, this is the flushing results browser, and this gives you 1 row per event. Tells you what the name of that event was, whether it was conventional or unidirectional, how much length of pipe did you flush during that time, how much length was involved, and then it's like how much more from the previous flush. Okay, so the previous flush already did 900 feet, and out of that, the next one does 1,600, but a lot of that was already flushed in the first one, so it's only 740 more feet of piping. What pipe had the lowest pressure in the system to make sure you're not run the pressure down too low? And these next 2 columns are only good for unidirectional, so don't worry about it. And this tells you what the flow is. For unidirectional flushing, it looks like the previous one, except under flushing type, it says unidirectional. And there are other numbers. It says, how long does it take to flush that pipe? Given that you have a certain flow going through it, you know the velocity, you know the length. So now you can figure out how long you should flush. And then if you flush that long, you know the diameter of the pipe, you can say how much water was involved. So that's what those 2 extra columns you get. Now that's the minimum number. Now what you can also specify is a safety factor, so that if you need to flush for 1 minute, you specify a safety factor of 3 and it'll give you 3, because usually you don't just want to just remove the water from that run. You want to remove the water from that run and then kind of flush it out really good behind it. So you don't really just want to flush for the minimum amount of time. You want to flush for maybe 2 or 3 times the minimum amount of time to get a good clean flush. Okay, and this is just another view. When you highlight one of these things, when you have the flushing browser open, you highlight one of the rows, you'll see these each run will be displayed. Okay, so then we get to the question of, well, I mentioned that some pipes are self-cleaning because the velocities every day are pretty high. So it's very unlikely that sediment is going to settle there. It's got high shear stress and or high velocity. So we actually have a network navigator query where you can say, okay, show me all the pipes that automatically exceed this certain target shear stress. And 0.1 is a good number for pounds per square foot units. I think it's around 1 for newtons per square meter. So you specify that, and we'll show you that certain pipes pretty much always have high enough shear stress. Okay, so those are the ones that show up here in the cyan colors that have, under a normal day, they're going to have enough shear stress that it doesn't really matter. Okay, and most of those are chronological. One here is coming out of and into the main tank. Some of the other ones are coming out of the pump station at a bottleneck point in the system. Others might be where you have multiple pipes going into a single pipe, or the velocities increase. So you're never quite sure. Sometimes you get surprises by which pipes should be self-cleaning in the system. Okay, that's sort of looking at the flush by flush. The other one you have is the Flushing FlexTable. Okay, in the Flushing FlexTable, this looks at things pipe by pipe. Okay, so after you've done a whole area, you go back into that area and you say, okay, which pipes did I successfully flush when I did this program? So it goes through and looks at all the flushes that you ran in that area, all the events, and say, okay, what's the one that got the highest velocity for that? So we say, okay, these are the flushing events that clean this pipe. So pipe P63 was cleaned by flush H12, okay, and pipe 70 got the highest velocity at H11W, and we also give it the highest velocity is. And if there's some pipes that didn't quite meet our standard, we'll flag them and we'll say it didn't meet the target velocity. Now, I said, what the most important thing though is not just to do this as a paper exercise, you sit in your office and play with the software. It's to get some kind of guidance out to the guys in the field who are going to do the flushing. Okay, so this is the flushing field report. Your notes have an earlier version of this that wasn't quite as good. We got some user input on it and we improved it. So this is the improved version of it. So if you look at the PDF that you got, it doesn't have this version of it. But what we show you is which hydrant are you going to flow? And we gave it a good name, end of Maple Street. Okay. Now some of the blank ones are ones where we want the operator to fill those in, write those in when he does this work, and he bring it back to the office and say, okay, this is what we have the predicted pressure, because usually when you get out there, you'll check the static pressure. Okay, so you'll see what it is, and we predicted it would be 24, and so you can check to see if that was what you got. And we predicted we get 730 GPM out with the model. If you have a flow meter on, one of the standard pitot meter, you can measure what the flow is out of the hydrant, and you could say, are we close to it? You may not get 730, but if you get 250, then you say, aha, something is wrong here. Maybe we closed too many valves or did something that was incorrect. So this gives the operator a little guidance on what to expect when he goes out there. And then we list which valve did you open to get this. This was a valve that was closed in the previous run. And then which ones did you close? Now, usually the way I recommend people do this is it should be the street name with the valve, the run of the valve is on, near the intersection. So this is Pine at Maple. So the pipe is actually running down Pine Street, and Maple is the intersection. So come up with good names though, or maybe it's in front of McDonald's or something like that. Something that the operators can find. In some systems, if you say isolation valve 18, they know exactly which valve that is because that's in their GIS. But in other places, you say isolation valve 18, and they look at you like, what are you talking about? So you've got to know how the operators want to see this results. And then we give them what's the minimum flushing time. And again, you could put a safety factor. And here you have a safety factor of 2 saying what's recommended. They have flush for 10 minutes in this particular example. And then we list also the pipe run to be cleaned. The operators really don't care that much about it. So that's why we don't really make a big deal of it. We do, though, on the next display, which shows you the pipe run that is being cleaned. Here, the red one is really the transmission main for the pump station fill in the tank. We don't worry about that one. We're cleaning the orange pipes. And we've done that by closing the red valves. And, this is one way to display it. There's a lot of different ways to display it. You've got one important thing that's much more important in this use case than it is in any other place where you're using the modeling is what kind of background map do you have? Okay, you've really got to think about that. Are you going to print this out in color or black and white? Now this graph here looks really nice in color. If you were to print this out in black and white and hand it to someone, it look like this blob. So you've got to really think about that as to what way is it being given to the operators. And you want to show all the roads. Like this happens to be a Google Earth image that was the basis for this. So this is what Martin and I were talking about just before the session. So this model was developed on top of Google Earth, and that's okay. That's a pretty good one. In some cases, you'd rather something like this. It might be a slice through the GIS that shows you street names, etc. So it depends on what the operators want and what you have available. So in this case, we've closed certain valves. We've show that flowed hydrant is green, and we show the closed valve as red. And you can also go through and have multiple views. So this one here is a zoomed view. So you could have a view of the whole pipe run that's being flushed. And then you could zoom in and attach views of every intersection where you're going to be doing valve operations. So you could have multiple of these images within any event. And we could also, have the operator write values in and give feedback as to, yes, we did this, and it get taken back and put into your asset management system as when was this run flushed. You put in all kind of cool stuff in here that you want. What was the flow you measured? What was the static pressure when you got there? What was the pressure when you ran it? And I'm surprised these guys got that pressure on the 0.2 psi. That's really good readings. Okay, and you can change the colors. If you don't like the colors we had, you can change them. We have that option. And this is just another example of what you flowed and what you closed for a given run. We don't actually do callouts like that. So let's review the steps involved in flushing. Okay, start off with by opening the flushing manager. It's analysis flushing. Create a flushing study and then create an area within the study. And specify the criteria. What's the target velocity or shear stress? Specify any auxiliary results you want, such as low pressures. And create the flushing event. Which nodes do you flow? And which events are going to be active during a run of an area? And then pick the other calculation options that we give you. Set the initial conditions. Make sure you have the right scenario as the representative scenario. Which pumps are on, which pumps are off when you're out there flushing. And so it's not so much, you should already have created that representative scenario, but if you didn't, you could create it and assign it to the area and compute. When you're done, usually I look at the flushing results table, see which pipes got high velocities. Then I could open up the flushing results browser and look at the individual flushes, and then look at each individual events. I could just step through them. It looks, just click, 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 and you can see the colors change. Which is the orange run here? This is the orange run in the next one. It's a very nice way to scan things. And if it didn't work out the way you want it, go back and keep trying. And when you're done, print out the report for the operators. Okay, some tips and suggestions in doing this. Good color coding is really helpful. Set up some good intelligent color coding. And usually what I try to do is, overall, when I'm done with an area, have a color coding by the maximum velocity that was achieved. Now, you're going to have some pipes that aren't going to get good flushes. So, for example, if you have a dead-end cul-de-sac with no hydrant at the end of it, that's not going to get flushed. So, there are going to be places like that, and you want to see those places. So if for a given run where you've closed the pipe, it'll show up as a gray pipe. I suggest you say the gray, and you can size the hydrants, make them bigger or smaller by how much flow you got out. Use demand as the value. And you just roll through the different events in your flushing results browser. The typical kind of events is that conventional flushing works well for dead ends and for looped areas that have one predominant direction of flow. If locations between the sources work, if you have multiple sources of water going into an area, you may want to basically isolate one source and have all the water coming from a certain tank or a certain pump station during the time you're out there flushing. So what some people do is at the start of the day, they'll kind of close off all the back doors to this area and feed from a certain direction. Remember what I said, flush with clean water behind you. So they'll figure out where's the clean water, close the back door feeds, and feed from that way while they're out there flushing. And when you have gridded areas, very highly gridded areas, you may need valve operation and unidirectional flushing to get any kind of velocity difference. If your system is very strong, if you have a grid of big pipes, you've got to close some valves to get a good enough velocity change. And if you're working with a 24-inch main or a 36-inch main, what do you think about flushing of those? Well, my experience is it just doesn't change the velocity much. I've played around this a little bit and caused floods before I really got any real velocity. So usually flushing is not appropriate for large transmission mains. If you suspect there's a lot of sediment in a large transmission main, you try to set up a day where you're running a really high velocity to see what kind of scour you get. Or you may need to go to something like pigging in order to clean out a large transmission main if you suspect there's a lot of sediment in it. Working with a sewer force main now where they suspect that they have a lot of sediment in the bottom of the sewer force main and they're going to have to probably pig it to get a clean pipe. Some interesting issues here. Here's a study I was working on where there's a pump station going to a tank and the hydrant we're flushing was pretty close to the pump station. So we assumed that the part of the pipe that we're going to clean was the area between the pump station and the tank. But we ran the model, and we're going to get about 800 GPM out of the hydrant. We ran the model, and it turns out that most of the water came back from the tank and not from the pump station. Now, why would you expect that? Well, the reason for that is the pump has to run on a curve. So there's a certain limit of the pump capacity. How much water could the pump put out? Well, a tank can put out as much water as you can pull from it. So a lot of times you get surprised when you're doing this flushing planning and the water doesn't move the way you thought it would. Sometimes you get these non-intuitive solutions coming out. So tanks tend to provide more water than pump stations usually. And here's a case now where you have 1,000 GPM going to this hydrant and it splits around the loop to the hydrant. Well, did UDF help? Well, if you're trying to clean the long run, it didn't really help much. If you're trying to clean the individual small runs, you can close one and flow through each of those and flip them back and forth. In this case here, we have flow from two different directions, from two very different directions. And you close one to get UDF. Well, if the flow came from a very different direction, it's probably not going to affect the flow from the other direction. So UDF might not help in that particular case. And this is why you run the model to see this stuff, to see what happens before you get out there and say, gee, we didn't get as much water as we thought. Run the model first of all and see. So now, so far I've been focusing mostly on flushing to remove sediment and turbidity and stuff like that. But flushing for water age or for disinfectant residual is kind of a little different animal. Okay, it's not quite the same sort of thing. So here, what your goal is not so much to get velocity, because velocity really doesn't matter that much. What you want to do is bring fresh water into an area. So that's a little different mindset. So velocity and shear stress aren't really as important. What's important is to look at what's the water age, or there's a good indicator, or chlorine. So what you would do first of all is run a long EPS to find out what's the starting point after we reach some kind of steady state in the system. So you run the model for maybe 2 weeks or so, and you save the results of that last one and make that the initial conditions for your flushing runs, because that's where you're starting from. You're not starting from a clean system. And you start going through and run flushing events just as events. Just set up an event. You don't have to go into a flushing manager. Just set up a new scenario that says, I'm going to open this hydrant and get so many with this emitter coefficient, and see how long it takes for fresh water to go into that area if you're increasing the flow. If you have 10,000 GPM coming in, the hydrant puts out 500, it's going to take a long time to flush that area. If normally, though, the flow into an area is 20 GPM, and you open up a hydrant and get 1,000 out, you're going to flush that area really quick and get fresh water into that area really quickly. So it really depends, again, on the relative size of how much water you're flushing versus how big of an area you're trying to serve. And you can just watch, by color coding the model by water age, you could just watch how fresh water moves into the system. It's really nice. You see the changing colors of the pipes as fresh water gradually moves into that part of the system. In these cases, UDF doesn't really help much. Now, it may help if you have water in the old water in the tank, and you don't want that old water from the tank getting into an area. That might help a little bit. Or if you're trying to drain a tank and bring the tank level down to get rid of old water in the tank, you can see that. And UDF might help, but usually it's not as important as it is when you're trying to get high velocity. Okay, so you can run the model and see which pipes have the lowest velocity. In this case, they're the gray pipes. Okay, there's a lot of gray pipes in this big system. We can then do conventional flushing and look at the velocities we get. And we're getting velocities around 6.8 as an average, just in case. So we're getting some really good velocities in here. And we're getting good water age results as well. Okay, so what we looked at here was the change in velocity during flushing. We see a lot of it has some big changes. The big transmission mains, of course, don't have much change, which is what you'd expect intuitively. And this just shows you what some of the output might look like. You can show which hydrants are closed and which hydrants you want to open, which valves are closed. Okay, so you can start flushing, and hopefully your hydrants don't look like the one in the picture, and you aren't being bothered by a big dog.
If you found this video helpful, please give it a like. If you want to see more such series, consider subscribing to our channel. Thank you, and see you next time.